Hey, so this video is going to depend completely on the last one, so I need you to make sure that you've watched that last one completely and you understand it really well before we get into this one. So we talked a lot about approximating derivatives using different schemes, forward, backward, centered, difference approximation schemes. Um, and what this lecture is about is kind of talking about the error associated with those approximations, because it's actually possible using Taylor's theorem to kind of pin down what to expect with regards to how far we're off in those approximations. When we're done with that, so we're going to do these derivations, but then we're also going to extend them to actually find a scheme for a second derivative approximation, and I think that is pretty cool. So why don't we get to it and start talking about this? So, as I said, when using these formulas to these difference approximations to approximate a function's derivative is what this really should say. Okay, we might naturally ask a question, which formula provides the best estimate? And it actually depends on the function in particular. We saw that a little bit last class. However, the centered difference approximation, as we kind of mentioned, as I kind of went over a little bit, tends to produce the most accurate results. And to explore this a little bit more closely and to see why this might be, we're going to turn to an old favorite, comes up a lot this semester. We've already seen it a bunch. It's Taylor's theorem. Okay, and as I said, we're going to be doing a few derivations, all of which depend on Taylor's theorem. So make sure you understand it. That's key. That's why it was in your warm-up. That's why, I don't know, it drives half of everything in this course. So good thing to know. Anyway, so Taylor's theorem tells us this, right? We have that f of x is approximated, right, centered at x0. We have an approximation. This here is a first degree Taylor approximation with some second degree error term. We went over this in the very first week. That c here is just some value. It depends on what value of x you sub into this function, and c is some value between the x and the x0. Okay, well, if we consider some x, x0 plus h, we can actually kind of write this in a different sort of way. So I'm subbing in x0 plus h, and all I'm doing is putting that right into this function. So this x becomes an x0 plus h right here. This x right here becomes an x0 plus h, but check this out. If I put in x0 plus h there, I get x0 plus h minus x0, which is just h. And see, this whole thing becomes nicer because now I just have an h in front of f prime. And the error term, similarly, is going to have h squared in front of it. And what we can do with this is rearrange this. So all I've done is plugged in a value, the center point plus a little bit, and we're going to find our finite difference scheme for the forward difference approximation, along with an associated error term. So let's do that. We obtain, let's isolate for the f prime of x0, and if we do that, we're going to get this. F prime of x0 is equal to f of x0 plus h, that's this term right here. I'm going to take this f of x0 and subtract that from both sides. So I'm going to get minus f of x0. I'm going to take this error term and subtract it off that side as well. And that gives me a minus h squared f double prime of c over 2. I'll put the 2 right here. And yeah, what do I need to do? I still have an h, right? This was an h right here, so I'm going to divide by that h in order to get that approximation. So I end up with, you know what? Let's do it on 2 lines. If I were to just rearrange this equation, I would get h f prime of x0 equals this stuff. And then I can divide by the h to get f of x0 plus h minus f of x0 all over h. And then this error term is going to be minus h over 2 f double prime at c. Okay, let's take a look at this for a sec. This part right here, this first part, this is our scheme, right? This is our forward difference scheme. So that's kind of cool. We can just grab that from Taylor's theorem. This here is error, and it looks really weird right now, so I'm going to redo the primes, but this was an F double prime at C. Don't be freaked out by that, right? C is some number between, well, it's x0 and x0 plus h, because that's what we subbed in for the x. So C is some number in there. We're evaluating a second derivative at that number. This is a constant. H over 2 times another constant. This quantity depends on h. That's our error term. And it grows the larger the step size is, right? Or it tends to. So this here is our error term. And even if we don't know exactly what the C is, I do know from our conversation on asymptotics and big O notation and stuff that that quantity there is big O of h, as h gets very small. And I'm using the h gets very small definition of big O because we're talking about a small step size, right? And we want to think about the error shrinking as that step size goes to 0, because once it is at 0, we should get the true derivative. Okay, so basically, we have found that the error kind of decreases along the same rate as a linear function, right? It decreases linearly to 0 as h goes to 0. So that's kind of cool, right? Taylor's theorem has the functionality of letting us kind of determine what error is associated with this forward difference scheme. And similarly, you can derive an error formula for the backward difference formulation, and I'm going to leave that for you to try. It's one of your for you to try questions. So, but it's very, very similar. It's not hard, but it requires you to kind of wrestle with that that formulation and Taylor's theorem and all that good stuff. So there's one more thing though. There's the centered difference approximation, and that one's a little bit weird, right? With the centered difference approximation, that was the one where we needed to take a step forward, subtract a step backward, and then we divided by 2h, right? It was f of x0 plus h minus f of x0 minus h over 2h. So that's really interesting because it never even involves x0 itself. So we have to be a little bit more creative. We need both. We need both of the quantities f of x0 plus h and f of x0 minus h to appear. If we want to get this from Taylor's theorem, we need to think about how to do that. Okay, so to make this happen, we do two different substitutions and then kind of work with both of them. So we're going to let x equal x0 plus h, so we'll substitute one value of x. We'll substitute in another value of x. We'll sub those into Taylor's theorem twice, and then subtract. Okay, so if we do that, we get, I'll do one of them, we'll do the other one. We have f of x0 plus h equals f of x0 plus h f prime of x0 plus h squared f double prime of x0 over 2 and h cubed f double prime, triple prime at some c value, I called it c1 here, and I'll tell you why in a second, over 3 factorial. That should be the same logic as before. All we've done is sub x equals x0 plus h into both sides of Taylor's theorem, no problem. So for the other one, I'm going to sub x equal to x0 minus h, thinking ahead and seeing that I need both of those quantities there. This will give me 2, and then if I have two equations that are true, maybe I can work with them and get our centered difference approximation scheme. So let's see here. If we substitute x equals x0 minus h in here, x0 minus h, I'm going to get here x0 minus h minus x0. And you can see how it's going to be a bit different, right? If I substitute in x0 minus h, the x0s will cancel, but I'm not left with h. I'm left with negative h. So I end up with f of x0 and then minus h, f prime of x0. Okay, let's substitute it into the next one. And I think you'll see that something interesting happens. For the squared term, if I go x0 minus h minus x0, these cancel. I get a minus h, but wait, because it's squared. So I do get a plus h squared. And it's going to be the case that every other one of these, all of the even powers, end up being squared out and become a positive. So I'm actually going to get plus h squared, f double prime at x0 over 2. And there's the error, and I'm going to write here minus h cubed. Same reason as before. If I were to sub that in here, I would get a minus that comes out. And I am going to write f triple prime at c2 over 3 factorial. So you might have a little bit of a question over why c1 and c2, but here's the reason. That c value in Taylor's theorem depends on the x, right? The c that you get is a number that is between the center point and x, whatever you sub in. And we've subbed in 2 different values of x, so I need 2 different values of c there. One of them's c1 between x and x0 plus h, and one of them's a c2 between x and x0 minus h, which necessarily have to be 2 different things. So I'm just going to write here, we need 2 different c's, c values, since these depend on the x we sub in. So that should make some sense, but it's really important. Okay, so that's what we get when we sub in. And here's what we're going to do. We're going to subtract these 2 equations. Essentially, I have 2 equations, 1 and 2, and we're going to get something cool. Look, by subtracting, we get something that looks like the numerator of that center difference approximation, if you remember from last class, f of x0 plus h minus f of x0 minus h. So that seems good. But what do we get on the right-hand side? Well, we have this one minus that one. That seems to be a full cancellation, so that goes away. We have an h f prime of x0 minus negative h f prime of x0. And look at what we get. We get a 2h f prime of x0. The second degree term, second order derivative here, h squared, these look like they're identical. They're also going to cancel. And we're left with these 2 things, which are going to be a bit different, but we end up with a plus. I'm subtracting, so I think I get plus h cubed over 3 factorial, because I've subtracted, so minus makes a plus, and I have to factor out those 2 derivative terms. So f triple prime at c1 minus f triple prime at c2, just like this. Okay, here's the magic. Think of the center difference approximation. It doesn't involve f of x0 itself. This term shouldn't be there, and it happened to disappear by using that sequence of I want to say creative operations to kind of get there. I also have f prime that's right here. Oops, f prime that's right here when I subtract those 2, and I know that I need that in my scheme as well. In fact, we have to solve for it. And check out what's attached to it. It's not an h, it's a 2h. So by doing this exact sort of thing, it's kind of like having the insight to do these things leads to this scheme. And we're going to have an associated error with that given by this term right here. So we're going to kind of build our center difference formulation from this. So that means I'm going to isolate for this thing. So I'm going to write that down. So we're going to isolate for f prime of x0 in a couple of steps. And in that first step, I'm going to take that 2h and divide both sides. So divide by 2h, and if we do, we end up with f prime of x0 equals, okay, let's see, if I divide by 2h, h cubed over h is h squared, there's still a 2, and a 3 factorial is 6, so I think we get a 12 on the bottom, don't we? We're going to get, oh, that's a plus, not an equals. And we're going to get an h squared over 12. F triple prime at c1 minus f triple prime at c2. Again, this looks like f1n. I don't know. I think I just drag my stylus on the tablet and it does that. Okay, and then finally we'll isolate for the derivative, and we're going to get here f of x0 plus h minus f of x0 minus h over 2h, and then with this ugly thing here, but that's minus h squared over 12, f1, 2, 3 derivatives c1, minus f1, 2, 3 derivatives c2. And what we find is that this is a scheme, our centered difference approximation scheme, and this is the associated error. No single step of this is tough, but knowing how this works means that you have to be pretty familiar, pretty comfortable with Taylor's theorem, and oftentimes there are people that are a little bit, hesitant about that, but practicing really, really helps. So I definitely urge you to go in and practice some of those derivations yourself and do the one that I left for you to try. So yeah, anyway, that error term is what we were interested in here. And you can see how it's different than the error term from what we had before. I don't know what the C1 is. I don't know what the C2 is. But these two things are third derivatives evaluated at some point. These are going to be numbers. The 12 is a number. I have h squared times a number. And we know from our experience from before, that is going to be on the order of h squared as h goes to 0. So the error is going to decrease quadratically rather than linearly as h gets smaller. So the error associated with that difference approximation has to shrink more quickly as compared to the other two formulations as h decreases. So that is why, so that doesn't necessarily say that the centered difference approximation will be better at any single step. But what it does mean is that as the step size decreases, the error associated with the centered difference approximation is much more likely to shrink quickly than the other two schemes. So it's kind of a that's the measure by which we're talking about here. So hopefully that makes some sense. And of course, I want you to talk to me if it doesn't. We have one more example to do for this lecture, and it's going to extend and give us a way of approximating a second derivative. And I will want you to know the scheme as well as how to derive it. So let's see. To do this, let's see. Considering a 4 times differentiable function f of x, use Taylor's theorem to derive a finite difference formula for the second derivative at x0. And I've given a little bit of a hint here that we will still need x0 plus h and x0 minus h. So we're going to do 2 different substitutions, and we're going to have to fiddle somehow to figure out how to do this. So why don't we start with Taylor's theorem itself. So Taylor's theorem, and we're going to be a little bit, I'll do the basic theorem in blue here. So we have f of x, 4 times differentiable seems a little bit nuts, but let's write it all out. F of x0 plus f prime of x0, x minus x0, and then we have plus f double prime at x0 over 2 x minus x0 squared plus f triple prime at x0 over 3 factorial x minus x0 cubed, and I'll write a 4th order error term associated with this. So plus f1, 2, 3, 4, get that, 4, evaluated at some c, x minus x0 to the 4 over 4 factorial. Okay. And again, I'll just point out that c is a number between x and x0. Whatever we're subbing in for x and the center point of this polynomial. So we're going to do these 2 substitutions. We're going to sub x equals x0 plus h and x equals x0 minus h, and we're going to see if there is some interesting operation that we can do in order to get out an expression for the second derivative this time. So far it seems pretty much the same as before. We've taken it one step further, assuming a 4 times differentiable function. But let's see where this goes. So if we sub x equals x0 plus h, that's going to be our first step. F of x0 plus h equals, okay, f of x0. This should be the same thing as before, right? This becomes an h. So h f prime of x0. The next one's going to be h squared over 2 Yeah, h squared over 2 f double prime of x0. I'm getting distracted by my primes again. This should be a double prime with the primes apart. They stick together. It's like, you ever tried to make, like, fresh rolls with rice paper and stuff, and if you try to soak them, and they touch each other, they stick to one another, and then you can't get them apart, and then you just give up and order takeout instead? Yeah, that's like these primes on this tablet. They just stick together for whatever reason. I think that like there's like a smoothing program that tries to get them together, or like tries to smooth out my. I don't want them smooth. I want them apart. Anyway, rant over. Anyway, let's see. Where was I? I'm substituting in x equals x0 plus h. So this is going to become an h cubed over 3 factorial, f1, 2, 3, and then finally an h to the 4 over 4 factorial, f 1, 2, 3, 4 at c. Okay. I substituted in something. I'm going to be doing a couple substitutions. So similar to before, I'm going to turn this into a C1 because it's going to be something that's different from the other one that I need. I can't call them both C. Okay, so that's cool. Let's do the other substitution here. X equals x0 minus h. By the way, fresh rolls are really, really good. Especially if you get a good, like, peanut, like, satay sauce. I don't know how authentic that is, but I could eat, like, 20 of those or so. Okay. So similar to before, subbing in the x0 minus h, it's going to cause the odd ones to have minus signs in front. So I get the same thing as I did on the last line, but with minus h, boop, boop, like this. I have a minus h cubed over 3 factorial, but the positive ones are going to stay positive. So, like we ought to as well. 1, 2, 3, 4, and I'm going to make this a C2. Okay, so we have to be a little bit creative. This is not like the last one. I don't want to subtract, because if I subtract, watch what happens. If I subtracted this first line from that second line, I have this quantity here and this quantity here. They're going to subtract away, and I'm not going to have any expression for my second derivative. And that's exactly what we're trying to find an approximation for. So it seems like a bad idea. Let's not do that. Instead, why don't we add? If we add the two together, we're going to get a different kind of expression. These will be preserved, and it's going to be other terms that kind of cancel out. So add the two together. And let's see what we get to. I honestly kind of enjoy these derivations because they're not too bad. They also test really well on like how well you understand Taylor's theorem. But they're not, I don't know, they're not awful. There's a little bit of rating, but okay, I'm adding this and this. That just gives me two of those. So I'm going to write down 2f of x0, like so. I'm adding this and this, and you can see that those are going to cancel out, so those go bye-bye. If I add 2 of the next one, I'm going to get 2h squared f double prime at x0 over 2, so it looks like the 2's are going to cancel as well. That's kind of cool. This next term is going to cancel because I'm adding, well, two things that are subtracting two things that are identical, plus this, plus minus that, right? So that's going to go away. And the errors, I think we're going to get here, h to the 4 over 4 factorial, and then the sum of those two. 1, 2, 3, 4 derivatives at C1, f 1, 2, 3, 4 derivatives at C2. Okay, so interesting. All of those, like the first derivative, the third derivative terms go away. And what we can do is start isolating for this second derivative term, because that's what we wanted to scheme for. So we wanted a scheme. So I know somebody's going to ask me, how did you know to do this? Well, it's from looking at what you need to do, right? If I know I want a scheme for the second derivative, it makes sense to do an operation to these different different lines here that's going to preserve that second derivative, and it's not subtracting, it's adding. And I've given you a hint on how to start too. So we wanted a scheme for f double prime at x0. So isolate for it. Let's see if we can fit it on this page. So I'm going to bring over all of the other terms other than that that term right there. So I'm going to get f of x0 plus h plus, oh, let's see here. I'm going to take this to the other side. So we get minus 2 f of x0 plus f of x0 minus h. And I'm going to bring that error term over as well. Minus h to the 4 over 4 factorial. f1, 2, 3, 4 at C1 plus f1, 2, 3, 4 at C2, like so. Well, I'm going to run out of room. I should probably be a little bit more careful of space, but C2 equals, this is h squared f double prime at x0. Okay, and what we're going to do is finish this off by dividing everything by h squared. So divide by h squared to finish. And it looks like we have f of x0 plus h minus 2 f of x0 plus f of x0 minus h over h squared. And it looks like this error term here is going to become an h squared over 4 factorial if I divide by the h squared with this here and this here. That equals f double prime at x0. And what we find is that we have our new scheme. This here is a scheme that approximates a second derivative, which is a new tool that we have. So scheme, I'll say this is the scheme, and this here is the error. And as we can see, it's on the order of h squared as h gets small. So we have a brand new scheme for approximating a second derivative using the same sorts of derivations that we did before. And it's interesting, right? The second derivative approximation scheme uses information from a step ahead, information from a step behind, but also information at the point that you're interested in. It uses f of x0 plus h, f of x0 minus h, but takes away 2 f of x0. And then it divides the whole thing by h squared. So that's really cool, actually. That means that if you have 3 data points, you can now estimate what the second derivative would be simply by using this scheme. And I think that's really fascinating because, well, it's obvious, right? Or somewhat obvious how you might estimate the slope. But there is also a way to estimate concavity. And that's what this gives us. And that's really interesting. And the associated error shrinks pretty quickly as that step size decreases. It decreases quadratically. Really cool derivations there. I think they're really important. So I would like you to practice them. Hopefully they make sense. And of course, as I said, everything relies on Taylor's theorem, which is, again, half this freaking course. So hopefully you found that interesting. We're going to be actually taking some of these concepts about approximating derivatives and using numerical methods associated with different calculus concepts and moving forward. So the next concepts we're going to talk about actually connect back to differential equations. This might strike fear into a few people's hearts. I know some people love differential equations very much. I love differential equations, but not everybody in the class has differential equations. But I want to say, don't worry about it. None of the methods that we touch are going to rely on any solution techniques from that course or those concepts. These solution techniques, these numerical solution techniques, are going to be usable by just about anyone who understands basic derivatives. And I will give you all the groundwork you need to have enough understanding to be able to go forward without any problem. So that's the goal anyway. And if you have any concerns, as always, there's my email. And yeah, until next time, thanks a lot for watching. Study hard and, stay positive through everything. And I hope to see you soon. Bye, everybody.